diffusion models dominate image restoration, but applying them to deblurring reveals a critical mismatch. Standard diffusion uses additive Gaussian noise, while blurring is a convolutional process. This means noise-driven diffusion generates intermediate states with no physical relation to the true degradation. They are mathematically convenient, but physically meaningless. ConvDiff replaces the noise operation with a convolutional trajectory derived directly from the blur kernel. The method operates in the frequency domain, where convolution becomes multiplication, y equals x times h sub blur. ConvDiff factorizes the blur spectrum into incremental steps using fractional powers. The modulated spectrum is defined as h to the beta of blur equals magnitude of h to the beta times e to the j phi beta, where beta controls degradation strength. This formulation is powerful for Gaussian blur. Since the Fourier transform of a Gaussian is also a Gaussian, fractional powers remain Gaussian. This guarantees that every intermediate state corresponds to a valid, real-valued, non-negative, and normalized blur kernel. Training uses a UNet with ConvNeXt blocks to predict the sharp image from a random state, sampled continuously from beta uniform 0 to 1. Inference is iterative and blind. The network predicts a cleaner estimate, and an iterative Wiener-based kernel estimation updates the frequency representation. H tilde equals y times x star divided by magnitude x squared plus s. On div 2k with Gaussian blur, ConvDiff achieves a PSNR of 29.59, significantly outperforming the noise-driven SR3 at 25.35 and INDI at 26.09. ConvDiff trails end-to-end SOTA methods like high diff, primarily due to error propagation in the iterative Wiener estimation. It is also limited to spatially invariant Gaussian blur, as the fractional power property depends on the Gaussian distribution, preventing direct use on motion blur. However, ConvDiff demonstrates that aligning the diffusion trajectory with degradation physics yields superior results. Future work targets learned kernel estimation and spatially variant blurs. To restore blur effectively, stop denoising and start deconvolving.